Power lines are ubiquitous, yet often overlooked. These towering structures are the unsung heroes of our modern world. They form the backbone of the electrical grid, silently transmitting power. Without them, our lives would grind to a halt. Power lines are not merely cables strung between poles. They're carefully engineered systems designed to withstand various stresses. The weight of the cables, wind loads, ice and bird strikes put immense strain on these structures. Engineers must ensure the grid's reliability and resilience. The electrical grid is a marvel of modern engineering. Power lines and poles are essential components of this intricate system. They are the arteries of our electrical infrastructure. When these structures fail, the consequences can be devastating. Blackouts, economic losses, and even loss of life can result from power grid failures. Therefore, it is crucial to understand the engineering behind these structures and the challenges they face. One of the most significant challenges in power line design is mitigating the impact of wind. Wind exerts force on both the cables and the supporting structures, potentially leading to oscillations, galloping, or even catastrophic failure. To combat this, engineers employ sophisticated modeling techniques to predict wind loads and design structures with appropriate strength and flexibility. Lightning strikes pose another significant threat to power lines. A direct lightning strike can deliver millions of volts to the system, causing equipment damage, power outages, and even fires. To protect against this, power lines are equipped with lightning arresters, which divert the electrical current to the ground, preventing it from damaging sensitive equipment. These devices, along with grounding systems and insulation, are crucial for ensuring the grid's resilience against lightning strikes. The height of power lines also plays a crucial role in lightning protection. The taller the structure, the more likely it is to attract lightning strikes. Engineers must carefully consider the height of power lines in relation to the surrounding terrain and the likelihood of lightning strikes in the area. Beyond wind and lightning, engineers must also account for other environmental factors such as ice accumulation, extreme temperatures, and even earthquakes. These factors can all impact the structural integrity of power lines and poles, and engineers must design structures that can withstand these challenges. The choice of material for power poles is a critical factor in their design and longevity. Wood, steel, concrete, and increasingly composite materials each offer a unique set of advantages and disadvantages. Wood poles, the traditional choice, are economical and readily available but susceptible to rot, insect damage, and fire. Steel poles offer greater strength and durability, but are more expensive and prone to corrosion. Concrete poles offer excellent resistance to weathering and insects, but are heavy and require specialized equipment for installation. Composite poles, made from fiberglass or other synthetic materials, offer a combination of strength, durability, and lightweight, but come at a higher cost. The selection of the ideal material depends on a variety of factors, including cost, environmental conditions, load requirements, and aesthetic considerations. Each material also requires specific maintenance procedures. Wood poles need regular inspections for rot and insect damage. Steel poles require corrosion protection, while concrete poles need to be inspected for cracks and other signs of deterioration. Composite poles, although more durable, are not maintenance-free and require regular inspections for damage and degradation. The choice of material also has environmental implications. Wood poles, while renewable, require harvesting trees, which can contribute to deforestation. Steel and concrete production have a significant carbon footprint. Composite poles offer a potentially more sustainable option, but their manufacturing process can also have environmental impacts. Extreme weather events can overwhelm even the most robust power grids. Ice storms, hurricanes, and earthquakes have caused catastrophic power outages, highlighting grid vulnerabilities. The 1998 ice storm left millions without power for days and weeks. Hurricane Katrina in 2005 caused widespread outages due to wind and flooding. The 2021 Texas winter storm highlighted the need for grid resilience. These events underscore the importance of grid modernization and resilience. Section 5. Learning from disaster, the evolution of grid resilience. Each failure provides valuable lessons, driving innovation and improvements in power line engineering. This knowledge leads to stronger materials and more resilient designs. Smart grids utilize sensors and automation to monitor conditions and reroute power. This allows for faster response times and reduced outages. The future of power grids lies in their ability to adapt and evolve. By embracing new technologies and prioritizing resilience, we ensure a reliable electricity supply. Section 6. The smart grid, a glimpse into the future. The concept of the smart grid represents a significant leap forward in power grid technology. Unlike traditional grids, which are largely passive, smart grids incorporate sensors, communication networks, and advanced control systems to optimize grid performance. This allows for two-way communication between utilities and consumers, enabling real-time monitoring of energy consumption and dynamic pricing based on demand. Smart grid technologies offer numerous benefits, including enhanced reliability and resilience. Self-healing capabilities and automated responses to faults can minimize outage durations and improve overall grid stability. Improved efficiency. Real-time monitoring and control can reduce energy losses during transmission and distribution, leading to a more efficient grid. Integration of renewable energy sources. Smart grids can accommodate the intermittent nature of renewable energy sources like solar and wind power, facilitating their integration into the existing grid infrastructure. Empowered consumers. Smart meters and home energy management systems provide consumers with greater control over their energy consumption, allowing them to manage costs and reduce their environmental impact. Section 7. The environmental impact of power lines. While power lines are essential for modern life, their construction and operation have environmental impacts. Land clearing for right-of-ways can fragment habitats and disrupt ecosystems. The manufacturing of materials like steel, concrete, and copper is energy-intensive and contributes to greenhouse gas emissions. Additionally, power lines can pose a collision risk for birds, particularly large raptors, and electromagnetic fields, EMFs, emitted by power lines have been a subject of concern, though scientific evidence of their health effects remains inconclusive. To mitigate these impacts, utilities and regulatory agencies have implemented various measures. These include minimizing right-of-way impacts, utilizing existing corridors, co-locating lines with other infrastructure, and implementing vegetation management practices that promote biodiversity can reduce habitat fragmentation using sustainable materials. Employing recycled materials, exploring alternative pole materials like composites, and promoting the use of renewable energy sources can lower the environmental footprint of power lines. Bird collision mitigation, installing bird diverters on power lines, marking lines to increase visibility, and carefully siting lines away from critical habitat areas can reduce bird collisions. Addressing EMF concerns. While the scientific consensus remains that EMFs from power lines pose minimal health risks, utilities can address public concerns by burying lines in populated areas and following established safety guidelines. Section 8. Public perception and power lines. Public perception of power lines can be complex and often negative. While recognized as essential for modern life, power lines are often seen as eyesores that detract from scenic views and lower property values. Concerns about EMFs, bird collisions, and the visual impact of transmission towers can lead to community opposition to new power line projects. Effective communication and community engagement are crucial for addressing public concerns and building acceptance for necessary infrastructure projects. Utilities can foster trust and understanding by providing transparent information, clearly communicating the need for new power lines, the rationale for route selection, and the steps taken to minimize environmental and community impacts. Engaging with stakeholders, holding public meetings, soliciting community feedback, and addressing concerns directly can help build consensus and identify mutually acceptable solutions. Exploring alternative designs, considering underground lines, using aesthetically pleasing pole designs, and implementing landscaping measures can mitigate visual impacts and enhance community acceptance. Section 9. Conclusion. The ever-evolving grid. Power lines and poles, despite their seemingly simple appearance, are marvels of engineering designed to withstand the test of time and the forces of nature. From the choice of materials to the calculations for wind loads and lightning strikes, every aspect of their design is a testament to human ingenuity. As we move towards a future powered by increasingly renewable energy sources, the electrical grid with power lines as its backbone will continue to evolve. The integration of smart grid technologies, the development of new materials, and the ongoing efforts to enhance grid resilience will ensure that we have access to reliable and sustainable electricity for generations to come. As we continue to rely on this essential infrastructure, it is crucial to appreciate the hidden engineering that keeps the lights on and our world connected.